Yeah. So let's continue with the lesson. Very good afternoon to all of you. So yesterday we have discussed the isomerism part of general organic chemistry, right? So how many types of isomerism are there? Can anyone tell me the types of isomerism? We discussed one of the type and what are the two types of isomerism? Can anyone mention the names in the chat box of two isomerism? So what are the two types of isomerism, my dear students? Structural isomerism and stereoisomerism, right? So these are the two types of isomerism. So yesterday we have discussed about the structural isomerism and we have studied four types of structural isomerism yesterday. So the four types were chain isomerism, position isomerism, functional group isomerism, and metamerism. So today we are going to look about the stereoisomerism, which is the second type of isomerism. Okay. So what is meant by stereoisomerism? The compounds that have the same constitution and sequence of covalent bonds but differ in relative position of their atoms or groups in space. That is, atoms having same molecular formula but different spatial arrangements. Okay. Molecules having same molecular formula but different spatial arrangement of atom is called as stereoisomerism. Okay. So there are two types of stereoisomerism as we have discussed yesterday. One is geometrical isomerism and the other one is optical isomerism. Okay. So now let us enter into the geometrical isomerism and see what it is. So the geometrical isomerism arises due to restricted rotation around the carbon-carbon double bond, which is due to sidewise overlap of the pure p orbital. So when two p orbitals overlap in the sidewise manner, they form a double bond, right? Example, if I take C2H4, the name of this formula C2H4, right? Which is called as ethene. So in this ethene molecule, if you see, we have double bond between the two carbon. Double bond between the two carbon. One is sigma bond and the other one is pi bond. So the pi bond is formed by the sideways overlap of the pure p atomic orbital, as you can see here on the picture. Now, the rotation of this pi bond is restricted. You cannot rotate the carbon-carbon double bond. Okay. So, because of this, a new isomerism called geometrical isomerism arises in the compounds. Okay. Now, what is the condition for geometrical isomerism to be exhibited by some compounds? The very first condition is the compounds must have carbon-carbon double bond, carbon-nitrogen double bond, and nitrogen-nitrogen double bond. Or it must be a cyclic compound. So this is condition number one. So geometrical isomerism exists only in these type of compounds. Okay. Both the atoms or groups joined with doubly bonded carbon must be different. So let me show you. So we have four groups attached to the carbon-carbon double bond, right? So at least two groups or two atoms must be different. Then only the geometrical isomerism exists in that compound. Okay? So at least two should be different. So A should not be equal to B. Okay? So example, carbon-carbon double bond attached with AA and BB. So if both the AAs are on the same side of the double bond, then it is called as cis isomer. If two similar components are on the opposite side of the double bond, then it is called as a trans isomer. Okay. So geometrical isomerism is otherwise called as cis-trans isomerism. So what is meant by cis? If the similar groups are present on the same side of the double bond, here you see Similar groups are present on the same side of the double bond. So it is a cis isomer. If they are on the opposite side of the double bond, it is called as a trans isomer. Got it? So these are the two conditions for geometrical isomerism. Now let us discuss one example based on this. The example that I have taken is but2ene. The formula will be like this. So 1, 2, 3, 4. Between carbon number 2 and 3, we have a double bond. And the total number of carbon is 4. So it is but2ene. Okay. So I have a double bond. I have double bond between carbon number 2 and carbon number 3. And to carbon number 2, I have one CH3 attached and one hydrogen attached. And to carbon number 3 also, I have one CH3 attached to this and one hydrogen attached to it. Where this is carbon number 1 and this is carbon number 4. Okay. So if the two similar groups are present on the same side of the double bond, if they are present on the same side of the double bond, then what is this? This is called as cis-but2ene. Okay. If you place the two similar groups on the opposite side, then it is a trans-but2ene. It is called as trans-but2ene. Is it clear to all of you? It is very easy. It is very, very easy. Okay. Can you all able to understand? Any doubt for anyone? Nandini, Pragati, Farnas, Chandu, Ajmala, Devananda. Can you all able to understand this is trans isomerism? Yes. So now let me give you one question. All right, all right. So draw the cis trans isomer of the following. So how will you draw? I have two compounds. Both of them are having double bond, right? So let me draw the compound A. Let me draw the cis and trans isomer of compound A. So I have two carbons, right? 1 and 2. So to the first carbon, chlorine is attached and hydrogen is attached. So the second carbon also the same thing. Hydrogen and chlorines are attached. If two similar groups are on the same side, it is cis. If you put them in the opposite side, it is trans. If you put the similar groups in the opposite position, then it will give you the trans isomer. Okay. Say similarly in the second compound also. This is carbon 1, carbon 2, carbon 3 and carbon 4. So draw the double bonded carbon, and if two COOH are on the same side, it is cis. If they are opposite, it is trans. Okay. So what is a very important condition to be followed? The groups, the four groups which is attached to the carbon-carbon double bond should be different. At least two among them should be different is the very important condition you should follow while drawing the cis and trans isomer. Okay. So this is all about the geometrical isomerism. The next isomerism is optical isomerism. So let us discuss about optical activity first, and then we will discuss what is optical isomerism. Okay. So what is optical activity? So let me take an ordinary light. Okay. I've taken an ordinary light. And I'm passing this ordinary light through a nickel prism. So if this ordinary light is passed through the nickel prism, the plane polarized light will be formed. So what is the difference between ordinary light and plane polarized light? Ordinary light will give light in all the direction, and plane polarized light will give the light only in one direction. Okay. So it is forming a plane polarized light. So that plane polarized light, you see, it can give light only in one direction. Now, if I ask this plane polarized light to pass through a compound, okay, I have taken a compound in the conical flask. If I am passing this plane polarized light through this compound, two things can happen. Okay, two things means either one of those two can happen. One is the plane polarized light can remain as such, or it can rotate. It can rotate. The rotation can be done in two ways. One is through clockwise direction. The first case is the clockwise direction, and we call this clockwise rotation as dextrorotatory. Okay, dextrorotatory. It can be indicated by a small letter D or by putting plus. So what does this plus denotes? The rotation in clockwise direction is represented by D or plus. And the other rotation is anti-clockwise rotation, which is called as levorotatory. Okay, levorotatory is denoted by small L or by putting minus. Okay, so these two types of rotation can be observed. This is the another case. If the compound that you have taken in the container is optically active, then you will observe the second condition. Okay, if the compound is optically active, you will observe the second condition. Okay, it means that there are two isomers, two compounds in the conical flask. So that's why one compound is rotating the plane polarized light through clockwise and the other one is rotating through anti-clockwise direction. Got it? So if the compound is optically active, it means that they are rotating in both the directions. So they are optical isomers of each other. Got it? So if your compound is optically inactive, if it is not optically active, then you will observe the first case. Got it? Optically inactive compound will give the first case, or I can say that the mixture is a racemic mixture. The racemic mixture will also show the first case, that there won't be any rotation of the compound. Got it? Optically inactive compound will show no rotation, and optically active compound will show two different types of rotation. One through clockwise and another one to anti-clockwise. Got it? Able to understand? So this is called as optical activity concept. Optical activity concept. Now, what are the conditions for a compound to be optically active? So we cannot go and do the experiments in the laboratory every time and find out the answer, right? In the examination, we have only the pen and paper with us. We have to find out the answer, right? Or we will be sitting in front of the computer and doing things. So in that case, how will you find out whether the compound is optically active or not? So you should follow the conditions which I am going to give right now. Condition number one is the compound must have at least one asymmetric carbon. What does mean by asymmetric carbon? Chiral carbon. So what is a chiral carbon? A carbon which is attached to four different atoms or groups is called as a chiral carbon. So here the central carbon is a chiral carbon. Why? Because it is attached with four different atoms or groups. A, B, C, D. Right? So this carbon is joined by four different atoms or groups. And all the four are different. A is not equal to B is not equal to C is not equal to D. So this carbon is a chiral carbon. Okay, if a compound is having chiral carbon, then that compound will be optically active. That compound will be optically active. Clear? I will give you some example. Listen, lactic acid. So if you look into the lactic acid, the central carbon of this lactic acid is chiral. You know why? Because it is attached with four different atoms or groups. It is attached with four different atoms. One is hydrogen and the other one is COOH. Third is OH and the fourth one is CH3. So it is attached with four different atoms or groups. So it is an example for a chiral carbon containing system. Got it? So this is first one. The second condition is compound must have non-superimposable mirror image relationship. Compounds must have non-superimposable mirror image relationship. Okay. So that isomer which rotates the plane polarized light towards clockwise direction, that is through right hand side, will be the D isomer, and if I take the mirror image of this, I will get the mirror image, right? If I take the mirror image, the rotation will be towards the left hand side, which is actually called as the L isomer. The compound must have non-superimposable mirror image relationship. So if I have a ball and if I try to take the mirror image of this ball, I will get the same picture in the right hand side also, right? Now try to place this above this ball. You cannot find the ball which is already here because it will go and get superimposed on the first ball. Okay. It means that there is no non-superimposable relationship. So one is placing over the other. So it is superimposable. Okay. If a compound is having superimposable relationship, then it is optically inactive. It is optically inactive. Okay. So if you take a, what to say, okay, I'll take a compound. I'll take a compound that I'll take a compound like this. And let me take the mirror image of this compound. So what I will get? CH and COH. So this remains as such, but OH will come here and chlorine will come on the other side, right? Now what you do, take the second compound and place it over the first compound. So above this Cl, OH will come and get placed, right? And above this OH, chlorine will be placed. So it is having non-superimposable mirror image relationship. So I can able to see the chlorine which is at the bottom if I place this molecule because above this chlorine we have OH, not chlorine. So I can clearly see the chlorine which is below. Okay. So if I can able to see a compound which is below the compound which I am trying to place, then it is very clear that the compounds are having non-superimposable. If they are having non-superimposable mirror image relationship, then the compound is optically active. Okay, this compound is optically active. So is it clear to all of you? So the two conditions are, one is the system should be chiral. It should have chiral carbon. And the second one is the compound should have non-superimposable mirror image relationship. Is it clear to all of you? Do you guys have any two condition? These two are very, very important. We will study about this optical activity in the upcoming organic chapters also. Okay, very good. So if you're having any doubt in between, please feel free to ask me and get it clear. Got it? Now let's go ahead with one question. Very easy question. How many chiral carbons are present in the following compound? How many chiral carbons are present in the following compound? So go for compound A first. So tell me how many chiral carbons are present in this compound. So try. Suhra is saying that we have 8 chiral carbon. No. Chiral carbon means the carbon should be attached with 4 different atoms or groups. How come 8 chiral carbon? Answer 8 is incorrect. Check once again. Check once again. You should not count the carbon atoms which is there on the straight chain. I am not asking you the number of carbon atoms in parent chain. I am asking you to find out the chiral carbon. Isharat is saying 3. Is 3 the correct answer? Listen. First of all, carbon number 3 and carbon number 6. These two are the chiral centers, chiral carbons. These two are the chiral carbons. Okay. So there are 2 chiral carbons present in this compound. I will explain. Yeah, Tausha, listen. So if I go for this carbon, it is having So if I take this carbon, it is attached with one methyl group here and ethyl group here. And we have one hydrogen because the carbon is having only 3 bonds around it. So the remaining is hydrogen. And we have one big group. So this is one. This is the another one. This is methyl. This is ethyl. This is a hydrogen. And on the other side, we have a big compound. So 4 of them are different, right? 4 of them are different. So the carbon which I have marked in by putting the asterisk is a chiral carbon. Okay. Is it clear? Is it clear? And coming to the second chiral carbon, this one, you see, this carbon is also having only 3 bonds around it. Is also having 3 bonds around it. So the remaining, the fourth one is a hydrogen. So it is chlorine, hydrogen, and here one isopropyl group, and here we are having the another big group. Okay. So 4 of them are different, right? 4 of them are different. So it is a chiral carbon. Clear? It is a chiral carbon. So the other carbons, if you try to check, if I go for this carbon, so this carbon is having only 2 bonds around it. So the remaining 2 are hydrogen. So 2 groups are same. 2 groups are same. So that carbon cannot be a chiral carbon, right? In the same way, if you try to look for the other carbons also, you will end up with the same thing. So there are only 2 chiral carbons in the first compound. Coming to the second compound, compound B. So how many chiral centers are there? You guys are saying that there are, Suhra is saying it is 3, Pragati is saying it is 2. Which one is the correct answer? What about others? What is your opinion? Taushia, Ajmala, Farnas. Farnas is saying 3. Okay, let's check. Let's check. Here also we have only 2 chiral carbon. Okay, so whose answer is correct? Ajmala and Pragati answer is correct. So there are only 2 chiral centers. Okay, chiral carbon can be given only for the carbon which is having single bond around it. If you are having double bond, then you cannot say that it is a chiral carbon. Okay, it's applicable only for alkanes, not for alkenes, not for double bonded or triple bonded containing carbon. Got it? Only these 2 carbons are chiral carbon. So because this carbon, if I take, it is having 3 bonds around it. The remaining one is the hydrogen. So 1, 2, 3, and 4. So 4 different atoms or groups are around it. It's the chiral center. Okay. So if I check for the next one, second chiral center, it is also having only 3 bonds. The remaining one is hydrogen. So OH, hydrogen, and here ethyl group, and here we are having one big group. Okay. 4 atoms or 4 groups. So it is a chiral center. Can you all understand now? Can you all able to understand? Why are the Farnas and Suhra have given 3 as the answer? You guys thought that this center is also a chiral center or what? It is not a chiral center, okay? Yeah. Now you have understood everything, I think. So this is how you have to find out the number of chiral carbons present in an organic compound. Okay? Yeah, because of double bonds, Suhra has thought. Yeah, I know, I know. No problem, my dear. So we are all learning. So today you have learned how to find it out, right? So hereafter you won't make the same mistake. So do you guys have any doubt till this? So here we are closing the isomerism topic. Do you have any doubts in isomerism? Structural isomerism and stereoisomerism? Pragati is saying no. What about others? Is it clear to all of you? No doubt. So please go and revise the isomerism. Okay. It's a very easy topic. If any question comes from isomerism, you can solve it very easily without wasting any time. Okay. The correct answer can be found out very easily. So please try to Learn the concept. So today I have asked you people to tell the two types of isomerism, but you guys did not tell me. No one has given me the answer for the types of isomerism. So if you are learning like this, then it will be very difficult at the end, right? So try to concentrate on the organic chemistry topics and study every day. Consistency is very important, right? So study every day. Now let's go for the next topic. Reagents in organic chemistry. Okay, I can tell that this is the second half of this lesson. Reagents in organic chemistry. So in this main topic, we are going to discuss what are electrophiles and nucleophiles, and the breaking of bonds topic, and reaction intermediates. So let me start with electrophiles and nucleophiles. Okay. And organic chemistry is the reaction between an electrophile and a nucleophile. Can you accept my statement? An organic chemistry is the reaction between an electrophile and a nucleophile. Whether you accept or not, this is the truth. Okay. The organic reaction is a reaction between electrophile and nucleophile. So it is very important to know what is an electrophile and what are the examples of electrophiles and what is nucleophile and the examples. Okay. Yeah. So let us study. Let us study that. So please concentrate more. Electrophiles are electron-loving species. Electro means electron. Phile means loving or liking or seeking kind of meaning. Okay. So electrophiles means electron-loving species. Clear? If it is loving the electron charge is negative, right? Electron charge is negative. If it is loving the negatively charged species, then it should be the positively charged one, right? Only then the positive can love the negative. So electrophiles are positively charged species. Positively charged species are electron deficient in nature. Positively charged species are electron deficient in nature. Clear? So what are electrophiles? Electron-loving species. Electron charge is negative. So electrophiles are the negatively charged loving species. So if something is loving the negative, then it should be a positive one. Okay, so electrophiles are positively charged one and it is electron deficient. Clear? Now let us study the types of electrophiles. There are three types of electrophiles. One is charged electrophile. So as I have already told you, electrophiles are positively charged species. So charged means here it is positively charged. So R plus, Br plus, NO2 plus, and NO plus. So all these positively charged species will fall under this category. Got it? And the second type is, so sorry, there are only two types. One is positively charged and the other one is electron deficient electrophile. Electron deficient electrophiles. There won't be any charge. The compound will be neutral, but it will be electron deficient. Okay. So they are also the electrophile. BH3, AlCl3, BCl3. And here if you see for aldehyde, RC double bond OH. So this carbon is the electrophilic center. And here for ketone, RC double bond OR. So this carbon is the electrophilic center. Got it? So these are the electron deficient electrophiles. So all of you should know the definition and the types with example. Is it clear to all of you? What are electrophiles? Electron loving species and the positively charged species and electron deficient species. Clear? Shall we go for the nucleophiles? Shall we go for the nucleophiles? Students, do you have any doubt in electrophiles? Am I audible? Okay. So the next is nucleophile. So what do you understand from the term nucleophile? Nucleo means nucleus. Okay. Phile means I already told you meaning is loving. So the nucleus loving species are called as nucleophile. Okay. Nucleus is positively charged. So they are electron rich compounds. Nucleus is a positively charged one. Okay. So nucleus is positively charged. So the one which loves the positively charged species are called as nucleophiles. So who will love the positively charged one? The negative only will love the positive, right? So the nucleophiles are negatively charged species and they are electron rich in nature. Okay. So lone pair containing compounds or pi electron containing compounds, they all will fall under this nucleophile category. Now let us study the types. The first type is charged nucleophile, the negatively charged nucleophile. Examples are Cl minus, OH minus, NH2 minus, HSO4 minus. Okay. So all these are the negatively charged nucleophiles. And the second type is called as lone pair containing nucleophiles. Examples are water, NH3, ROH, RNH2. Okay. So in all these compounds, we have lone pairs, right? So water, oxygen has two lone pair, nitrogen will have one lone pair, and alcohol, oxygen will have two lone pair, and amine, nitrogen will have one lone pair. So through this lone pair, they are all acting as an electron-rich center containing compounds, and they act as a nucleus. Okay. The third type is the pi electron cloud containing nucleophile. So the molecules which contains the pi bond, they will fall under this category. That is double bond and triple bond containing compounds will fall under this. And through their pi electrons, they act as a nucleophile. Clear for all of you? Electrophiles and nucleophiles are just the opposite of each other. Okay. Any doubt? Okay, my dear students. So now let's enter into the second topic. The second topic is breaking of bonds. Breaking of bonds. Bond can be broken down in many ways. Okay, many means two different ways. One is homolytic breakage or homolytic cleavage, and the other one is heterolytic cleavage. So you all know the meaning of homo and hetero, right? So let us discuss one by one. First, let me go for homolytic cleavage. What is meant by homo? Can anyone tell me the meaning of homo? What is the meaning of homo? Guys, what is the meaning of homo? I have already told you many times the meaning of homo. So none of you know the answer. Yeah, very good. Very good, Prahati and Suhra. It is same. Homo means same. Okay, homo means same. Very good. Very good, Farnas. So let me take a molecule in which A is bonded with another A. Okay, A2 is the molecule. So there is one bond between the two atoms of A. If this bond gets broken down, the two electrons which is present in that bond, one will go towards the first A and the other one will go to the second A. So what will I get? I will get A dot and A dot. So there are two electrons in a bond, and since both the atoms, both the bonded atoms are same, the bond breakage will be like this. It will break in a One electron will go to first A and the other electron will go to second A because there is no electronegativity difference between the atom. Okay, so the breakage will be done like this. So we get to A dot. Okay. Now the electron movement is shown by curved half-headed arrow. You all can be able to see, right? It is like a fish hook arrow. I did not draw the double-headed arrow. It is a single-headed arrow. Fish hook. All of you might have seen the fish hook, right? It is like this. So it represents that only one electron is moving towards that particular atom. Okay. The fish hook arrow denotes that only one electron is moving towards the particular atom. So the one electron containing species are called as radicals. One electron species are called as radicals. So radicals are formed by the homolytic cleavage of bonds. Got it? Now, when do this type of homolytic cleavage occurs? In which type of reaction? So what is a reaction condition for a bond to get cleaved like this? So this type of reactions can be initiated by radiation. Radiation means above the arrow in some reactions you can see H nu, okay, or heating symbol kind of thing. Okay. So when you see H nu or heating symbol like this above the arrow or below the arrow, then you should know that radicals are formed from such type of reactions. Okay. So this is one of the initiator. The second initiator is called as peroxide. Pragati, radicals are single electron containing species, my dear. Radicals are single electron containing species. They are formed if a compound is exposed to sunlight. Sunlight will have UV radiation, right? Ultraviolet radiation. So we denote that as H nu. H nu is called as packets of energy. Okay, packets of energy. If a light energy or heat energy is given to a compound, radicals are formed. Okay. For example, if I have Cl2 molecule, this is Cl2 molecule. And if the Cl2 molecule is exposed to sunlight, so the one electron will move towards one chlorine and the other one will move towards another chlorine. So I will get Cl dot plus Cl dot. So each one is called as a radical. Got it? Yeah. So the first initiator is sunlight or heat, light energy or heat energy. The second is peroxide. If you find some peroxides, hydrogen peroxide, H2O2, sodium peroxide, Na2O2. So if you find any peroxides in your reaction, then you can say the product is a radical. Okay. The third thing is when you heat the compound up to 500 Kelvin, obviously radicals will be formed. If you are heating a compound to a very high temperature, radicals will be formed. Okay. So these are the three initiators for which the radicals are formed from a particular compound. Is it clear? So the homolytic cleavage of bonds leads to the formation of radicals. Homolytic cleavage leads to the formation of radicals. And this is the very important point you have to keep in your mind. The radical is one of the reaction intermediate. Radicals are one of the reaction intermediate. So this is the homolytic cleavage. Pragati, all these things will be formed from a chemical reaction only, my dear. We are talking about the chemical reactions only. All these will be formed for a chemical. Yeah, in lab also. In lab also, if you are using a peroxide, you can form the radicals inside the lab, in the atmosphere, okay, in the ozone layer, everywhere radicals are formed. Okay, but they are not good for health. If you are getting exposed to radicals, it will enter into your body, okay, and it will do some chain reaction, okay, chain reaction will happen inside your body and it will lead to cancer. Got it? So the radicals are not good for us and also it is not good for the atmosphere. Got it? That's why we should reduce the usage of AC, refrigerator and all. Because the components, the chemicals which are coming out from the AC and the refrigerators, they have the capacity to form the radical in the atmosphere, which is actually not good. Got it? All right. Now let us go for the second type. Heterolytic cleavage of bonds. You guys said that homo means same. What is meant by hetero? What is the meaning for hetero? Very good. Different. Homo means same. Hetero means different. Correct. Exactly correct. Now for heterolytic cleavage of bonds, I am going to take a molecule whose formula is AB. Okay. AB. Now both the bonded atoms are different. Got it? One is A and the other one is B. Suppose, let me take B is an electronegative atom. If B is an electronegative atom, the two electrons which is present in this bond will move towards atom B, right? So what is meant by electronegativity? The tendency of an atom to attract the shared pair of electrons towards itself. If B is an electronegative atom, then B has the tendency to pull the electrons towards itself. So the electron which belongs to A will also come towards B and they will form A plus and B minus. Why A is getting positive charge? Because it is losing its electron. That's why it is forming a cation. And since B is gaining the electron, it is taking the negative charge. Got it? So we are getting two different types of intermediate from here. So here the electron movement is shown by curved arrow, normal arrow only. Okay, double-headed arrow. Because both the electrons are moving towards one atom, right? So we draw a double-headed arrow. So we are getting ions. Here ions are formed from this. One is a cation. A is a cation. Positively charged species are called as cations and negatively charged species are called as anions. The ions are formed from the heterolytic cleavage. And this type of cleavage is initiated by polar solvent. Number one is polar solvent. Polar solvent means water. Water is a polar solvent, right? In water we have H plus and OH minus ion. So it is initiated by polar solvent. And if you give the heat also, this type of ions can be formed. But it is a very rare case. But if you use any polar solvent, you can you can get the cations and anions. Got it? So how many intermediates we have seen? Three. One is the formation of free radicals. Second intermediate is a cation. Third intermediate is anion. The first one is formed by homolytic cleavage and this remaining two are formed by the heterolytic cleavage. So these are the three reaction intermediates. Three reaction intermediates. We are going to study about these three intermediates in a very detailed manner in the next slides. Okay. So let us enter into the topic called reaction intermediate. Reaction intermediate. So how does these intermediates form? How does these intermediates form in a chemical reaction? So in a chemical reaction, I have a substrate. Substrate is called as a reactant. Substrate is actually a reactant. Okay, in organic chemistry, we call the reactant as substrate. So substrate is a reactant and a reagent will come and attack this reactant. Okay, and because of this, we will get a transition state. And so, in some cases only we will get transition state, not in all the cases. Okay, and the transition state will be converted to intermediate. And again, the intermediate will be transferred to another transition state. And finally, it leads to the formation of product. So let me show this in a diagrammatic form. In a graphical form, let us discuss. So you see here, reaction coordinate versus energy is the graph. Okay. So initially what we have a substrate and the reagent. After some time, we are getting a transition state. Transition state 1. Okay. Transition state means at that point only the reactant and the substrate got activated. Reactant and the substrate got activated. And after some time, the intermediate is formed, then transition state 2, and finally we are getting the product. Okay. Clear? Now let me give you some information about transition states. Transition states are high energy compounds. High energy containing compounds. Right? You can see here. The energy of both the transition state is very high compared to intermediates, reactants and products. So since the energy is very, very high for those species, they are highly unstable. They are highly unstable and they cannot be isolated. Very good, Nandini. Correct. It is unstable and they cannot be isolated. You cannot separate the transition state compound because it will not exist for long. Okay, only if a compound is stable and if it is existing for long, you can isolate it and put it inside a container. Since they are highly unstable, they cannot be separated. Okay, they cannot be isolated. So these are the 2 points about transition state. Now, what is intermediate? They are relatively more stable compared to transition state. Intermediates are little bit lower in energy. They are little bit lower in energy compared to transition state, right? So they are relatively more stable. I'm not saying that intermediates are highly stable. Intermediates are relatively more stable and it can be isolated. It can be isolated. Got it? So now we are going to study about this reaction. 3 types of reaction intermediates. Free radicals, carbocation, carbanion. If the positive charge is present on the carbon, it is called as carbocation. And if it is present on the carbon, then it is called as a carbanion. Okay? Is it clear for all of you? So let me discuss about the first reaction intermediate alone today, and the remaining 2 things we'll discuss in the next class. All right. So the very first intermediate is free radical. So this is the structure of a single electron is present on carbon, then it is called as a carbon free radical, CH3 dot. CH3 dot. And you all know that radicals are formed by the homolytic cleavage, right? It is formed by the homolytic cleavage of bonds and it is electrically neutral in nature. There is no plus or minus. So they are electrically neutral and it has one unpaired electron in its p orbital. It has one unpaired electron in the p orbital and it is highly unstable. Hybridization of free radical will be sp2. You all know sp2 hybridization, trigonal planar in geometry, right? Can you all able to see the trigonal planar geometry? So this is the plane. This is the plane. Okay, trigonal plane. So it is occupying the trigonal planar geometry by having sp2 hybridization. And they are electron deficient in nature. It is electron deficient. And around this carbon, we have 7 electrons, right? How many electrons we have around this carbon? Each bond contains 2 electrons. 1, 2, 3, 4, 5, 6. And also in the p orbital, we have 1/7 electron. So around this carbon, we have 7 electrons. Only if there are 8 electrons, the compound is stable. And we can say that they are electron precise. If it is less than 8 electron, then they are electron deficient. So since the carbon free radical is having 7 electrons around it, it is electron deficient in nature. And as it requires only 1 electron, it is not considered as a Lewis acid. Only if a compound requires more number of electrons, we can say that the compound is a Lewis acid. Since it requires only 1 electron, It doesn't matter that much, so it is not called as a Lewis acid. Is it clear to all of you? So the very important points that you have to keep in mind is it is formed by the homolytic cleavage. Then it is neutral, unstable. Hybridization is important. Okay. And trigonal planar geometry, I said no, that is important. Is it clear? Electron deficient means it is having one electron less, right? That's why it is called as electron deficient, Pragati. Carbocation will also be electron deficient. 2 electron less, but here 1 electron less. So that's why. We will discuss about the positively charged compounds in the carbocation part. That is also electron deficient. This is also electron deficient. Is it clear? Is it clear? Okay. Okay, fine, students. This is enough for today. This is enough for today. No, Pragati. It won't have plus one charge. Free radicals will have only odd number of electrons around it. It will not have plus one or minus one charge. Okay. Plus one, minus one, they are all anions and cations. Don't get confused with the radicals and the cations. Okay. Clear? So let me write the formula for you. Listen. This is CH3 dot. CH3 dot is a radical. CH3 plus is a carbocation and CH3 minus is carbanion. Do you understand? So these two are electron deficient and this one is electron rich. Clear now? Is it clear? Okay. So thank you so much, students, for listening to today's lecture. We will meet up in the next session. Take care. Bye-bye. So please revise the topics that we have discussed so far in general organic chemistry lesson. Okay. Thank you. Bye. Thank you.